So let us see how to make a transmission gate in Microwind. So first of all, what is a transmission gate? So a transmission gate is just like a switch where we have a PMOS connected to a NMOS like this. Where the drain of the PMOS is connected to the drain of the NMOS and the output is taken over here. This is the input, let's call it X. So this let us say we'll just call it S bar and this is S. In this what happens is, so when that S is, let us say 0, okay, so when S is 0 then S bar is 1. So when S is 0 and S bar is 1, so the PMOS is also off and the NMOS is also off. So that means that the X is not transferred to Vout. So the gate is closed. And when S is 1 and S bar is 0, then both the gates are on and the switch, the transmission gate hold as is on. So let us see how to make a stick diagram for this. So first we'll have NMOS, then a PMOS. Then there are two different polysilicons in this one and they are not connected to each other. Then there is a connection over here, the source of both of them are connected and the drain of both of them are also connected. So this over here is S bar, this is S, this over here, this is X, and let us say this is just Y. So this way a transmission gate works. So let's make this in Microwind. So first we will need a N diffusion N well. So since we have to make a 4x12 P diffusion, so we'll make a N well of 16x24. Then let's put a P diffusion inside this. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 4x12. Let's also give this a poly. Let's zoom out so that we see more of this. Let's also make the NMOS as well. So we'll put N diffusion of 4x12. We'll give this one poly as well. In this, just make sure that the polysilicons are not connected to each other, because they have different signals going through them. One has S and the other has S bar. We can give them contacts. And the drain and source are also connected. Let's give a VDD to the N-well. Let's give a wave over here. So let us say we call this X. This over here. Let's call this S. We will just give the inverse of last clock loop here. So this would be S bar. Let us see the output over here. So when we run this, so now over here, as you can see, when S is 1 and S bar is 0, the transmission gate is on. We are getting the same waveform as X. The X and Y, the waveforms are matching. That means the gate is on. Now what happens is, actually over here the output does not go back to 0 because it stays in a high impedance state when the gate turns off. So when S is 0 and the S bar is 1, the transmission gate is turning off. So that's why we can see the waveform of Y is not duplicating the waveform of X. But it is not 0. It will be something like this. It can be 0 as well, but it can be something like this as well, which is high impedance. But this doesn't mean that the gate is on. The gate is off because we don't get the waveform of X at the output. Over here we can see that when the S turns on again, the waveform X is replicated on Y. So as we can see, this is how we can make a transmission gate in Microwind.